All right, today we're gonna cover chapters 5 and 6, and then whatever you have questions with, we can cover them next week. All right, to begin with, we have to remember what we did in chapter 2. Chapter 2, section 3, we did composite functions. For example, if I had two functions, f of x is that, g of x is this. The composite function were these: the Fogg and Goff functions. What this means is, the way you read this is the function f of g of x. Whatever is after the word of goes inside the other function. So this first function can be written as that: f of g of x. The second one is g of f of x. What this means is the g of x goes inside the f of x. So this equation, anywhere I see an x in the first one, goes in. That's what this means. So instead of 2x plus 3, that's what the function f is, I have 5x minus 2 plus 3. And I work it out. 2 times 5 is 10x. 2 times negative 2 is negative 4. Combine like terms. Negative, positive, 4 is bigger, so it's negative. 4 minus 3 is 1. So f of g equals 10x minus 1. Likewise, the other side. Now, what this one says is the f function goes inside the g. That means this equation, the f function, goes in place of x in the g. 5 times 2x plus 3 minus 2. Work it out. 5 times 2 is 10x. 5 times 3 is 15. Minus 2. 15 minus 2 is positive 13. So that's that answer. We have to know how to do the composite functions because this is where we'll test what we do this today. So that jumps us into section 5.1. Inverse functions. An inverse function says this: if a function is 1 to 1, I'm going to use this symbol from now on, 1 to 1. If a function is 1 to 1, then it has an inverse. And the inverse functions are noted by that negative 1. To find an inverse, it really only has 4 basic steps. First step, change f of x to y. Remember, f of x is equal to y, so we're just changing the way it looks. Second step, switch x and y in the equation. Then solve for y. The y that you just solved for is the inverse. Let's see this. Let's do an example. Find the inverse. Remember the steps. Change f of x to y. Switch x and y. And then solve for y. So we add 3 to both sides. X plus 3 equals 2y. Divide by 2. So we have y equals x plus 3 over 2. But this is our inverse. To test if your function is an inverse, we use the one-to-one test. The one-to-one test says this. If f of A equals f of B, then A equals B. That's the one-to-one test. So we have our function f of x equals 2x minus 3. We have to show this. We're assuming that f of A equals f of B. So here's our function. So we have 2a minus 3 equals 2b minus 3. Because in place of x, I put a and b. And work them out. Add 3 to both sides. 2a equals 2b. divided by 2, A equals B. So basically, if that's true, then we know we have an inverse. All we have to do is find it. Graphically, an inverse function is simply a reflection of the original function across the line y equals x. Okay, so what is that? If we have a graph, let's say the graph looks like this, and it crosses through 3. This is our function. If it has an inverse, the graph of the inverse, the line y equals x is this diagonal line here. For every x, this is 1, 1, 2, 2. So since this one, the original function crossed at 3, the y-axis at 3, and I folded across, it's now going to cross at 3 on the x. So our function will look like this. Our inverse function. In other words, if you just took your piece of paper, you drew your original graph and folded it across this line here, and you press down really hard, you'd get a copy of that image. You get the inverse. Well, what if we had, let's look at what they really mean. If I had, let's say, 4 points, 3, 1, 5, -2, 7, 0, and 8, -1. You first have to ask yourself, is that a function? Remember how we did that? We had 2 tests. We had the vertical line test. And then we know that all x's must pair with different numbers, different y's, y numbers. Remember also, so in other words, what it says this is if all your x's are different, then it is a function because it is one-to-one. If all of your x's are different, then you have a function. All right. So what does that mean? What does inverse function really mean? The first step of finding the inverse was switch the x and y's, right? That's what we do here. This is x, that's y. So I now get this. So I switch the x and y components of each point. So all we did was switch the x and y's, switch the x and y's. If you think about it, this point here is at 0, 3. The inverse would be at 3, 0, which is there. So that's exactly what we do. All we do is just change the points. To test graphically if a function is one-to-one, we use the horizontal line test. The horizontal line test simply says this. If a horizontal line crosses the graph of f of x more than once, it is not one-to-one. Then it doesn't have an inverse. So again, for example, is this function one-to-one? It is a function because it passes the vertical line test, but it's not one-to-one because the horizontal line test crosses the graph twice. that means the inverse function doesn't exist. Because if we look at the inverse function of this, we'd get that. And that's not a function because the vertical line test fails. Did we go over how to actually test them? Okay. Let's go ahead and find the inverse of that function. F of x equals x squared. Find me the inverse. What's my first step? Very good. Y equals x squared. Next step. Switch x and y. Now, we have to get rid of the square. The way we get rid of the square is square root. And that whenever you square root a square, you get a plus or minus. So y equals plus or minus the square root of x. But if you look at, this is the inverse. If you look at the graph of this one, it's a square root function. Remember, the square root function looks like this. Positive and negative, so it looks like this. That's not a function because the vertical line fails. So x squared is not 1-to-1. So its inverse does not exist. But we can make it exist. The reason this fails is because our domain of f of x squared is negative infinity to positive infinity. It fails the horizontal line test. But what if we got rid of this side and change the domain from negative infinity to positive infinity to just 0 to infinity? So now we only look at x squared from 0. So this part here. The inverse of it now would be the square root of x, which is how we remember it. All right. So that's if the function's not one-to-one, you can redefine the domain to make it one-to-one. Tests to determine one-to-oneness. I just say space saying that. Test to determine if it is one-to-one. If I give you a function and we find the inverse of that function. So let's see. 2x minus 3, switch x and y. Solve for y, we got x plus 3. So the inverse of y equals x plus 3 over 2. Now, how do we know for sure if those are inverses of each other? This is how. Composite functions. So what that says is take the inverse function, put it in place of the first one. So this equation goes in place of x of the first one. 2x plus 3 over 2 minus 3. The 2's cancel, so we have x plus 3 minus 3. The 3's cancel, so we just have x. Try the other way. F inverse of f. That means I take this function and anywhere I see an x in the second one, I put it in its place. So then 2x minus 3 plus 3 over 2. So let's fix the top. Negative 3 plus 3 cancel. The 2's cancel. We're left with x. That's the test. The test is this. Since you see they both ended in x, to test if they're really inverses, this has to be true. They both have to equal x. That does it for section 1. Now section 2, exponential functions. Until now, all of our equations that we used want to look like something like this, where x, what we call the base, and we had a number as the exponent. So we did this before. Now, things have changed. The variable is the exponent, and the base is a number. So an exponential function looks like this. F of x equals a to the power x. But we have stipulations for the base, a. A has to be positive, and a cannot equal 1. Those are the conditions. So since a has to be positive and it cannot equal 1, we have 2 distinct sets of numbers we can use. The graph of a exponential a to the power x remember, a has to be positive. That means all of our answers will be above the x-axis. You can never have a negative answer. A cannot equal 1. So anything to the power 0, if x is 0, if x is 0, anything to the power 0 is equal to 1. So we always have our y-intercept at 1. The graph looks like this. Was 2 to the power x. Remember, let's say we had -4. If x was -4, a negative exponent simply means it becomes a fraction. Two to the power 4 is 16. So it's 1/16. So it's got to be pretty small. If it's over here at +4, 2 to the +4 is +16. So here it goes very high. So what this says, we have two things to look at. Remember, A has to be positive. So if A is between 0 and 1, in other words, if A is a fraction, it crosses through 1, it's a decreasing function. Or if A is a decimal or a fraction, the graph looks like this. If A is greater than 1, it crosses through 1, and it's an increasing function. The larger A is, the faster it grows. The properties of an exponential function. It's continuous, meaning there's no breaks, no asymptote. Well, like I said, there's a horizontal asymptote. The horizontal asymptote, you'll see in a second. The function is 1 to 1. It satisfies the horizontal line test. The domain is from -infinity to +infinity. The range from 0 to +infinity. It's an increasing function if A is bigger than 1. It's a decreasing function if A is between 0 and 1. The horizontal asymptote is 0, the x-axis. And the y-intercept is 1 at the point 0, 1. Transformations occur the same way we've been talking about in the past. So the graph of 2x looks like this and crosses through 1. So if I have 2 to the power x minus 2, that belongs together. This is a horizontal shift, since the change happens on X. From chapter 1 or chapter 2, we saw that the horizontal shift always the opposite sign. So it's 2 to the right. There's my new origin. I shifted the origin from there to there. It still crosses at 1, so the graph now just shifts over 2 spaces to the right. This is a vertical shift because after you do the X and the 2X, we have a vertical shift. It goes down 4 spaces. 1, 2, 3, 4. All that means is our origin shifted from there to there. Remember the graph originally crossed at 1? There's 1 space above the x-axis. So in our new case, the y-intercept is 1 above the x-axis. So it's at -3. How about this one? Remember, if the base is between 0 and 1, it's a decreasing function. And it's negative, so that means I flip it across the x-axis. And now graph looks like this. An application, a very important application of exponential functions. Compound interest. Whenever you buy a house, a car, or anything big ticket item, you'll be faced with compound interest. And here's the formula. So A stands for what's called an annuity. That's the amount owed. P stands for principal. The amount borrowed. R is the rate you borrowed the money at. it's given in percent. We have to switch it to decimals. N is the number of times interest is compounded. T is time in years. N is a difficult one. N depends on if N is yearly or annually, then N equals 1. If N is monthly, then N equals 12. If it's weekly, then it's 52. Daily is 365. So it all depends on how often it gets compounded. Just plug them in there. You have to use a calculator. Now, there's our formula. A gentleman by the name of Euler decided, hey, what if I borrowed $1 for 1 year at a rate of 100%? Decimal wise, that's 1. It's 1.0. So what his equation came up to be is this. And as n goes to infinity, as n gets bigger, this number approached a specific number. It got really, really close to this number, 2.71828182824, blah, 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 blah. It became a constant, which is what we call Euler's constant. E. E stands for Euler. 2.71828 and blah, blah, blah. We'll be using this shortly. So it's an exponential equation. It looks the same way. It behaves the same way as everything else. But it's used more often in businesses and in engineering. All right, that does it for that section. Section 3, we got to pick up the pace. Logarithms. Whenever you see the word log, that means logarithms. Logs are the inverse of exponentials. This is what it looks like. The normal, this is read the log of a of x. What it means is this. This is what it's asking. What power do we raise a to equal x? That's what it means. How about this one? Log base 2, oops, the log base a, that's what it means. I'm sorry, I'm sure that. This is your base. So log base 2 of 8. What power do we have to raise 2 to equal 8? Two times 2 times 2 is 8, so it's 3. What power do we raise 10 to equal 10,000? 10 times 1 is 10, 10 times 2, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So it's to the power of 4. How about that one? What power do I raise 5 to equal 5? Yes, excellent. So if these numbers are ever the same, it equals 1. Another trick question. What power do I raise 5 to equal 1? Anything to the 0 power equals 1. We can convert between logarithms and exponential equations. Log base a of x equals y. Remember, a is still the base. When we do the conversion, it has to remain the base. What happens is this. This base pushes up the y. Since the base is gone, it just has x. So there's the conversion. So far, so good? So if, like, for example, if I gave you log base 2 of 8 equals x, convert that. Yeah, so this base comes over here. pushes the x up, and the log drops off, so we have 8. Remember, we figured out that it was 3. When we did it up here, we said 2 has to be raised to the power 3 to get 8. So how do we get that? What is 8 made up of? 4 times 2, it's 2 times 2 times 2, isn't it? Or 2 to the 3rd power. The bases are the same. The only way they can be equal is if the top numbers are equal. So x is equal to 3. There's a problem. Your calculators cannot solve this problem. Because the only buttons your calculator has on them are these. And I'll discuss those in a second. So in order to find what this answer is, we have to use what's called change of base. So we start off with this equation. And we have to use one of these 2 keys in the calculator. So it's going to give you the same answer. So let's use the first one, log. So log of this number goes on top over the log of the base. The ratio is going to be the same. You type those in your calculator, it'll give you the answer to this question. You can also use the ln. Whatever's on top goes on top. Whatever's in the base goes on the bottom. They'll give you the same answer because it's the proportions that's the same. Like this. Well, if you have a calculator, you just type it in there and it'll give you the answer. As I'm saying is, you can't solve this on a calculator. So in order to get the number, the actual physical number, you have to change the base and then type it in the calculator. The graph of the log. Remember, the log is the inverse of the exponential function. The exponential function looks like this. It crosses through 1. It's at 0, 1. So that means this is the e to the power x function. So our other function has to cross at 1, 0. It looks like this. So the logarithmic functions will look like this. Three types of logs. Depending on the base. So the first one, let's say base 10. Our counting system is base 10. It's decimal, 10 from 0 to 9, from 10 to 19, from 20 to 29. It always grows in groups of 10. We call that a common log. In other words, since it's our base 10 system, whenever you see this is log base 10, because it's a common log, you don't have to put anything down there. So for example, here in this example, this one was log base 2, which didn't exist in our calculators. So we switched it to the log base 10, common logs. The common log of 8, common log of 2. The next one, base E. Remember Euler's number? We call that a natural log. So a log base E will look like this, ln x. So if you ever see an ln x, that means it's log base E. And then base anything else. Anything else, you're going to have to put that number on the bottom. You have to write it out. All right, let's look at the properties of logs. The first one is called the product rule. The log of a product of multiple elements. No matter how many you have, whenever you multiply them, you can split them up by putting a plus between them. Because when you multiply, it makes things bigger. That's why we add them. The quotient rule. If I have a fraction of terms, then you subtract them. The top number minus the bottom number, the log of the top minus the log of the bottom. The power rule. You cannot have exponents in logs. So whenever you have an exponent inside of log, that exponent goes out in front. and the special rules. We talked about these earlier. If the base and the number are the same, that equals 1. The log of anything that equals 1 is 0. So let's look at this. Here's some examples. Expand this one. Because you notice that this is just one big equation. Using the rules on top, whenever you have fractions, that means it'll be a subtraction, right? So here's the rule. If you notice, anytime you have a fraction, whatever's on the bottom will have a minus sign in front of it. Whatever's on top will have a plus in front of it. So this one, there's 2 on top. We have x to the 4th plus y to the 3rd. And the ones on the bottom have a minus in front of them. Log z squared minus log m cubed. So whatever's on top will be plus, whatever's on the bottom will be minus. You can't have an exponent, so all the exponents go out in front. So we have 4 log x, 3 log y, minus 2 log z, minus 3 log m. What if I gave you this? What would be the final answer? Remember, you cannot have an exponent, so that m goes in front. Since these are the same numbers, that equals 1, so the answer is just m. How about that one? ln is log base e. Can't have an exponent. Since these are the same, that equals 1. The answer is 3. So in other words, if you have ln of e, it's just that. If log base a, if here's a shortcut. So in other words, if the numbers are the same here, the answer is just the exponent. Also, another special one. because if the base is a of the big equation and the log is base, these cancel out. We just have x. All right, let's look at some examples, and then let's finish up the chapter. Let me see some examples here. Oh, here it is. Well, before we get to this one, let's look at this one. 3x equals 27. Our first plan of action is try to get the same basis, if at all possible. 27 is 9 times 3, which is 3 times 3 times 3. 27 is 3 cubed. Since the bases are the same, the only way they can be equal is if we have the exponents are equal. That's called the base exponent property. If ax equals ay, then x has to equal y to be true. Another property. Log base a of m equals log base a of n. Since they're both log base a's, the only way they can be equal is if n equals n. That's called the property of log equality. So if the logs are the same, then the operations have to be the same. All right, so let's look at our example here. 20 is not a base of 3. Here's another type. If we can get them base the same, that's great. If we're the same exponents, the same bases, great. But here we have a problem. X is the exponent, different base. So the way we do this is, since this is the only one that has an x, we can take the log base 3 on both sides. So this would cancel out. So we just have x equals log of base 3 of 20. Since our calculators don't have base 3, we do a change of base. And there's our final answer. That's what you type in the calculator. How about if we had something like this? They both have x's. So since they both have x's as exponents, I can't use log base 3 or log base 4. it would only work on one side. So I pick a neutral one. Let's say either pick ln, either natural or common logs. So we'll take the ln of both sides. Remember, it's the property of logarithmic equalities. So the exponent goes down. So we have x plus 1, ln 4, x ln 3. We're trying to solve for x, remember? So we have to get rid of the parentheses here. Distribute. So we have x ln 4. 1 times ln 4 is ln 4 equals x ln 3. Get all the x's on one side. So I subtract x ln 4 from both sides. Since I'm solving for x, they both have an x in common, so I can factor out the x. And divide by ln 3 minus ln 4, both sides. And there's your final answer. Any questions? Is there anybody waiting to come in? Anybody outside? I think we're the only people in the school. So, okay with this process? It's very heavy algebraic. I'm going to send out videos of more detailed step-by-steps. It's just I want to cover all this stuff. This is the end of chapter 4 or chapter 5. The only thing left we have to do is chapter 6, and it's not that difficult. You remember ever doing systems of linear equations? I'll show you.